One of the most popular techniques for model selection is cross-validation. And maybe one of the reasons why it's so popular is because it's very simple, very easy to understand, and it's also fairly general in terms of the number of situations that you can apply it. So the setup for cross-validation, it's the supervised learning setup. We've got some data, some x's and y's, x1, y1, up to xn, yn. And we are going to assume that we have some class of models. So m will be the value for a particular set of parameters for describing a particular model, and we assume that m takes it's from some finite class of models. So let's just number the models 1 to c. So we can always just number them. They're from some finite set. So for example, m could be, if you were doing regression with basis functions, linear regression, m could be the number of basis functions that you're going to use for your model, or it could be like in a k nearest neighbor classifier. It could be k for how many neighbors you're going to look at. And also though, so here we are assuming it's from a finite set, but what if you wanted to have, what if your class of models had a continuous valued parameter that was controlling the model complexity? Well, one thing you could do would just be to like discretize the space. But that'll only really work for smaller, lower dimensional, like if you had one parameter. And so in higher dimensions for continuous valued parameters, cross-validation is not really going to work very well, because you would have to have too many discretizations of too many discretized points in some high dimensional space. So we want to choose one of these models that's going to do well, for this problem. And if we're thinking from a decision theoretic point of view, which we are, then we want to minimize our expected loss. So we assume some loss function, L, and we want to minimize the expected loss for a new y and x. So we have some prediction function f, and let's subscript f by m to denote the f that we would get from the mth model on the data set D. So f also depends on D here, but I'm not making that sort of explicit. And we want to choose m to minimize this quantity. And we're assuming, so let's call this epsilon sub m, epsilon for error. Think of this as sort of a measure of error. And we're assuming here that x and y are random variables, distributed according to some probability distribution p, some true probability distribution that is unknown to us. Unknown. So this is the true probability distribution, and we want to minimize our expected loss under this true distribution. So this is not the p that we're using for our model. We might have some probabilistic model that we're using to model this data, but this p is the true. So this is the true distribution. Because that's what we really want to minimize our expected loss for, right? For the true thing. So how are we going to do that? Well, let's do a little thought experiment first. First, let's say we had our data here. Let's rewrite it again. x1, y1 up to xn, yn. And let's suppose that we also had, somehow, magically, we had some test set. Let's call it x prime 1, y prime 1, up to x prime t, y prime t. Some test set. And suppose that these were, our data were drawn IID from this distribution P, and that also the test set was drawn IID. This was a sample that was drawn IID from this distribution, from this true distribution P. well then, we could do the natural thing. We could train our model. We could, for each of these models M, we could train our model on the data set D, and then test it on the test set and see which one had the smallest error, which one had the smallest epsilon M. And then we could choose the one with the smallest error, and we would happily go on our way, and that would be our model M. But we don't. But this is just an imaginary thing. We don't have such a test set. But of course, well, we have. This is essentially the same as this, right? So why not just split up? So let's split. So let's take our data set. So let's take our data set here, and let me draw this as just a sort of block, so I don't have to keep writing x1, y1. So let's just visualize this as a block. Like this would be the first point, x1, y1, x2, y2, x3, y3, and so on. And then the training set over here, that thing's going to be, let's make that red. That's this other thing over here. But we can see D, that's what we get. And let's mimic the test set thing. Let's split this, say maybe here, into a validation set. We call this the validation set, and over here, all the rest, a training set. And then we could train, for each of the models M, we could train it on the training set and then evaluate its performance on the validation set, and then do the same thing. Choose the one with the smallest empirical error on the validation set. And that is called, so let me make a little space here, that is called validation. So let me say option A, validation, or sometimes people call this true validation. That's a little bit misleading, but that's sometimes what it's called. So all of this stuff is what we can see, and all of this we can't see. This is just imaginary, and this is called the test set over here. So we have training, validation, and test. So if that's validation, what is cross-validation? Well, it might occur to you that there's something a little bit, this is all fine and well. We can do this, and this will give us some measure of the performance of each of these each of these models M, I should say. There's C of them. Each of these models M. But if you might think, well, hey, what if just by chance one of the models tended to do really well on this validation set, but it wasn't really a good model in general? We could just get sort of unlucky, and this particular split might not be representative. And so, why not do a bunch of splits? And that is the idea behind cross-validation. Cross-validation. So what is cross-validation? Well, let's take this, so we have our data set D here. Let's redraw this down here again. So this is our whole data set, 1 to n. And the first step in cross-validation, let's keep that in green, I guess. So step 1 is permute the data. Randomly permute. I'll not put randomly. So you randomly permute the data. Randomly permute. I will put randomly. So we get another. I'll redraw the data set down here, and it's going to be permuted. So each of these points goes to a new location, and so on. So you shuffle the data randomly. That's step 1. And step 2, we're going to split the data into k folds. So we need to choose some there. This cross-validation has a parameter k. So this is going to be k-fold cross-validation. And let's say, for purposes of illustration here, let's say that k is 5. So we get this permuted thing. This is just the same thing here. And we split it into 5 equally sized parts. So if n was 100, then these would each have 20 points. And this is called fold 1. This one is fold 2, fold 3, fold 4, and fold 5. So each fold is a subset of 20 points. In this little example, where if n is 100 and k is 5, then each fold has 20 points. But in general, they're equally sized, or you try to get them as close to equal as possible. Equally sized subsets that divide the whole data set D into k different parts. So we've split it into these k different folds, and now comes the validation. So 3, we're going to do a series of rounds. So let me draw a matrix here. So we have this matrix, and each row in the matrix is going to be a copy, well, notionally, it's not, just sort of for visualization purposes, is a copy of these 100 points. And we split it, so we have, I guess I can go ahead and draw the different folds. So in each row we have a copy, and this is always, so this is fold 1, fold 2, fold 3, fold 4, and fold 5. So this is fold 1 here, first row. This is fold 1 also. It's the same points. This is fold 1. This is fold 1. This is fold 1. I just have 5. I've made 5 copies of the data. And now we have rounds. This will be for round 1, round 2, round 3, round 4, and round 5. The number of rounds is always equal to the number of folds. And now, so remember before, for validation, we had our training set and our validation set. And now, our validation set, let's make a little more room. On each of these rounds, there will be a different fold for the validation set. So in the first round, this one will be validation. The second round, so in the first round, fold 1 is the validation set. In the second round, fold 2 is the validation set. In the third round, fold 3 is the validation set. And then 4 for 4 and 5 for 5. Validation set. And for fold 1, all of the rest, everything else is the test. So all of this, fold 3, 4, and 5 is all the training set for round 1. So we take fold 2, 3, 4, and 5, we lump them all up together into one big set, and then we train on that, and then we're going to validate on this. Okay. All right, so I'm out of time in this video. I will finish sort of sketching this in, and then we'll pick it up in another video. Okay, see you soon.